So yes, it is pronounced L'Hôpital's rule. It is spelled like La Hospital's rule.
Yes.
But we are going back to limits. And this is an alternative method you can use to find limits compared to how we found limits before. So what I have at the beginning with these 4 examples, before I officially talk about what L'Hôpital's rule is, I first want you to know that you cannot use L'Hôpital's rule for every single limit. So it is not something that can always be used. Your limit has to be in a specific form in order to use it. So if we look at example 1, and we're going to review some ways we found limits before. So it says find each limit if possible. So we have the limit as x approaches 1 of x squared minus x over x squared minus 1. Whenever you evaluate a limit, what should you do first? Yep, plug the value x is approaching in to see if you get an actual value. So if we plug in 1, direct substitution, on top we would have 1 squared minus 1, that's 0. The bottom we would have 1 squared minus 1, that's also 0. So we got 0 over 0. That's an indeterminate form. So what did we say back in chapter 2? What did we have to do in order to evaluate this limit? Yep, try to cancel things out, rewrite it, simplify it. How would we simplify this expression? Take out an x, so factor. So we have the limit as x approaches 1. On top, I can factor out an x to then get x minus 1. What about on the bottom?
X plus 1.
Yeah, difference of squares, factors to x plus, oh, one of these is minus, sorry. One of those is x minus 1. So then the factor of x minus 1 cancels out. So you just have the limit as x approaches 1 of x over x plus 1. Then you use direct substitution, and we would get 1 over 1 plus 1, so 1/2 is the limit. Okay, so that's how we found limits before that were in, this is one case of an indeterminate form. One method we used was factoring. So then if you look at example 2, where it's the limit as x approaches 1 of the natural log of x over x minus 1, if I use direct substitution, so plug in 1, what is the natural log of 1? 0. And then 1 minus 1 on the bottom would be 0. So I still get 0 over 0. However, you cannot rewrite this like we could number 1. So we had different methods for rewriting a function, but we don't have a way to rewrite this. So I'm just going to make a note for right now that we cannot rewrite. So we have an indeterminate form. It doesn't mean the limit doesn't exist, but the methods we learned in chapter 2 cannot be used to evaluate that limit. Okay? And then if we look for 3 and 4, I included 2 limits where you have x approaching infinity. So just as a reminder, when you have an expression, a rational expression like in number 3, if x is approaching infinity, positive or negative, how do you work with those limits to evaluate them? Because you can't plug infinity in. Lydia? Yes, in the denominator. So I look at the denominator, highest power is x squared. So I would have to, on the top, divide everything by x squared. On the bottom, divide everything by x squared. So I would have the limit as x approaches infinity of, it will equal 1/2. So I'd have x squared over x squared, which is 1, minus 1 over x squared. And then 2x squared over x squared is just 2, plus 1 over x squared. And anything that is still over an x, as x approaches something very, very large, these terms will approach something very, very small. They will approach 0. So then your limit is just 1/2. Okay, so if we look at 4, and I also, I want to point out with 3, this is also an indeterminate form to begin with. So I know you can't substitute in infinity, But if you think of substituting in a very, very large number, so if I have a large number squared minus 1, that number is still very, very large, so the top would be approaching infinity. On the bottom, I have a very, very large number squared times 2 plus 1. That's still very, very large. So this is a different type of indeterminate form. If you just thought of substituting in a large number, you'd have infinity over infinity. We can't say that equals 1, like if it was 3 over 3, and you can see the limit's 1/2 anyway. But that's another indeterminate form, just like 0 over 0 is indeterminate. So for number 4, if we have the limit as x approaches infinity of natural log of x over x minus 1, so again, we can't substitute infinity in, but if we think of substituting in a very, very large number, what would natural log of x approach if x approaches infinity? Infinity, so natural log of x would become infinitely large. And then on the bottom, we would have a large number minus 1, which is still very large. So again, we have infinity over infinity. But it's the same expression for number 2. We can't rewrite this like we could rewrite number 3. So again, we're kind of stuck as to where to go from here. So this is kind of the why there's even the L'Hopital's rule and why you need to know it.
Little hospital.
It can't be used all the time. So you have to know when you can use it and then how to use it. You can only use L'Hopital's rule if, so it says, suppose f and g are differentiable, g prime of x is not equal to 0 near a except possibly, this should be possibly, not possible, possibly at a. And then suppose that, so if you have the limit as x approaches a of f of x over g of x, if you get an indeterminate form of 0 over 0, or positive or negative infinity over positive or negative infinity. So it has to be an indeterminate form, one of these two types. Then you can apply L'Hopital's rule, which states, so this is the actual rule. So it says that the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime. So you take the derivative of the top and the derivative of the bottom, and then you take the limit of that quotient. And that's if the limit on the right side would exist or is positive or negative infinity. So what I do want to point out is you are not performing the quotient rule on f over g. You're taking the derivative of the top and the derivative of the bottom separately. It's not the quotient rule. So what I want to show you for for example 5, this is the same as example 1. Here we found the limit the way we learned in chapter 2. I want to show you how we could find that limit using L'Hopital's rule because it is quicker, in my opinion. So if we applied L'Hopital's rule, and usually if I'm applying it, I'll write after it, like along the equal sign, I might put L apostrophe H to show I'm using L'Hopital's rule. But again, we already know this because we looked at example 1, but you want to check first if you have an indeterminate form. So I know if I plug 1 in, I have 0 over 0. So L'Hopital's rule can be used. And to apply L'Hopital's rule, I still have the limit as x approaches 1. But now I'm changing this expression by taking the derivative of the top and the derivative of the bottom. So the top was x squared minus x. What's the derivative of the top? 2x minus 1. So the top is now 2x minus 1. The bottom was x squared minus 1. And what will the bottom be now? What's the derivative? 2x. Okay, so I took the derivative of both. Now plug in 1. And I get on the top, 2 times 1 minus 1 is 1. On the bottom, 2 times 1 is 2. And here's my 1/2. Okay, that's quicker than, I mean, the factoring we had to do wasn't that time consuming, but I would say this is quicker. You can only use it, though, if you get 0 over 0 or infinity over infinity. What?
Like, why do you take the derivative of the top and the bottom? Like, why does it make sense that you do that? Because it's like a small difference.
Right, that would involve going through the proof. I'm not going to do that right now.
Dang. Sorry.
We'd have to look at the proof to see why it makes sense. I'm glad you're wondering why it makes sense. So there is a proof of why it makes sense. Now I realize I forgot to put the copier on the darkest setting, so this is very light, so I apologize. But I'm revisiting then the two examples from the front that we couldn't do. So example 2 was the limit as x approaches 1 of natural log of x over x minus 1. So on the front side, we couldn't evaluate this. We said if we use direct substitution, we got 0 over 0. But now with L'Hopital's rule, we can find the limit. So I'm applying L'Hopital's rule. So I'd have the limit as x approaches 1 of what's the derivative of natural log of x? 1 over x. And then the derivative of x minus 1 is just 1. So now if I substitute 1 in for x, I have 1 over 1 over 1. It's just 1. It is a complex fraction. Your limit is 1. Okay? And then for 7, limit as x approaches infinity of natural log of x over x minus 1. This was example 4 on the front. So again, we had looked at this and said as x approaches infinity, the top would approach infinity and the bottom would approach infinity. And I do want to say, when you have infinity over infinity, they do not have to be the same sign. So for example, if one of these was approaching negative infinity, L'Hopital's rule would still apply. So they don't both have to be approaching positive or both have to be approaching negative. They can be opposite signs and it'll still work. So if I apply L'Hopital's rule, I have the limit as x approaches infinity of, so we're going to have the same derivative we had above. Natural log of x is 1 over x. X minus 1 derivative is 1. So then if x is approaching infinity, what does 1 over x approach? 0. Because you have 1 over something very, very large. So that would be a very, very small number that would approach 0. Okay, so then what I did is I just included a bunch of examples that just some different things work out with the examples I chose here. So the next one, limit as x approaches infinity of e to the x over x squared. So again, first make sure that you have an indeterminate form of 0 over 0 or infinity over infinity. You can't use L'Hopital's rule if you don't have one of those two forms. So if x approaches infinity, what does e to the x approach? Infinity. E to the x would get infinitely large. What does x squared approach? Infinity. Okay, so we can use it. So this becomes the limit as x approaches infinity of, what's the derivative of e to the x? And then derivative of x squared is 2x. Okay, so now if you substitute in, again, a large number, if x approaches infinity, we still have e to the x on top. That still approaches infinity. What does 2x approach? Infinity. It's still indeterminate.
So you can do it again.
Yes, so we can apply L'Hopital's rule again.
Oh my God.
So you may need to use it more than once, but you have to make sure after the first derivative you took that you still have an indeterminate form. So I'm still going to have e to the x on top. The denominator is now derivative of 2x, which is 2.
Well, now it's going to be.
So now e to the x approaches infinity, 2 just approaches 2, and infinity, a large number divided by 2 is still large, so it approaches infinity.
My boy.
So you may need to apply L'Hopital's rule more than one time. All right, so then example 9, limit as x approaches infinity of natural log of x over the cube root of x. So if x approaches infinity, natural log of x, we've already said in previous examples that also approaches infinity, what would cube root of x approach? If x approaches infinity?
No, it'll be infinity. I'll keep it bigger, right?
So the cube root of a very large number would still be large, or if you think of the cube root function, the graph looks like this. So as x approaches infinity, the cube root of x would also approach infinity. So then I do have an indeterminate form. I can apply L'Hopital's rule. So I have the limit as x approaches infinity of, we said the derivative of natural log of x is 1 over x. And then the derivative of the cube root of x.
1/3 x is negative 2.
So cube root of x is x to the 1/3. So derivative is 1/3 x to the negative 2/3. What was that? So what I would do is I'm going to change, first of all, I'm going to keep this as 1 over x over, so this, if I rewrote it, would be, I'm going to keep the power of 2/3 but put it in the denominator, so it would be 1 over 3x to the 2/3. Because what I want to show you is now if you leave it like this, and you think, okay, if x approaches infinity, what does 1 over x approach? A small number, so this would approach 0. And what would 1 over 3x to the 2/3 approach? That would approach 0. So now you'd have 0 over 0. So you might think, oh, we could use L'Hopital's rule again, which you can. You don't have to, though, because this can be simplified. Yep, so you could multiply by the reciprocal of the bottom. So then your denominator is gone. So dividing by a fraction is the same as multiplying by the reciprocal. So then you'd have the limit as x approaches infinity of, and you'd have 3x to the 2/3 over x. Okay, so that still is not the form you wanted in because you still have infinity over infinity. But now what can I do with the exponents for x? I can subtract them. So I have the limit as x approaches infinity of 3, and then I have x to the power of 2/3 minus 1, which is negative 1/3, which I could write limit as x approaches infinity of 3 over x to the positive 1/3. And now I no longer have an indeterminate form, but I can say what the limit is. What would this limit be? If x approaches infinity, this would approach 0, because I'd have 3 over some very, very large number to the 1/3 power, which is still going to be large in the denominator, so this is 0. So that one, yes, was more simplifying than the rest. But still, using any of the methods we learned in Chapter 2, you would not have been able to find this limit. The methods we learned there would not have worked for that limit. So L'Hopital's rule would be the way to find the limit if you were not able to graph the function and use a graph to find it. All right, so then for number 10, limit as x approaches 0 of x plus tangent of x over sine of x. Tangent of 0 is 0. So on the top, if we plug 0 in, we do have 0 plus 0. And sine of 0 is also 0. So we do have an indeterminate form. So apply L'Hopital's rule. We have the limit as x approaches 0 of
1 plus secant squared x, and then over negative cosine x.
not negative cosine x, just positive cosine x. All right, and then now try substitution again, see if it works. So on top, secant of 0. So secant is the reciprocal of what?
Cosine.
Cosine. What is cosine of 0? 1. So the reciprocal of 1 would still be 1, and 1 squared is still 1. So secant squared of 0 is still 1. So you have 1 plus 1 over 1, so your limit is 2.
That's a lot of words.
All right, for number 11, limit as x approaches pi from the left. So L'Hopital's rule can still be used with one-sided limits, again, as long as you have an indeterminate form. So we have limit as x approaches pi from the left of sine of x over 1 minus cosine of x. So if we use direct substitution, what is sine of pi? Sine of pi is 0.
Life of pi.
Cosine of pi is negative 1. So this is 0 over 1 minus negative 1. And 1 minus negative 1 is not 0, it's 2. So this limit is 0. L'Hopital's rule, if you used it, would give you a wrong answer because it cannot actually be applied. You have to have 0 over 0 or infinity over infinity in order to use it. So don't forget about direct substitution. Don't just immediately jump to rewriting or using L'Hopital's rule. It doesn't always apply. Okay, but 12, so here we have the limit as x approaches 0 of tangent of x minus x over x cubed. Does it apply here? So we already said tangent of 0 in example 10 was 0. So we have 0 minus 0. And then over 0 cubed is 0. So we do have 0 over 0. We can apply L'Hopital's rule. Limit as x approaches 0 of. Derivative of tangent of x we said was secant squared x. Minus derivative of x is 1 over derivative of x cubed, 3x squared. Okay, now if we plug in 0, it's still,
Undefined.
well, secant squared of 0, we said up in example 10 was 1. So 1 minus 1 is 0. 3 times 0 squared is still 0. Now, for this one, say that again. Oh, for the derivative of secant, you're thinking? So you'd have to know that secant squared is really secant of x quantity squared. So you said 2 times secant of x times the derivative.
We don't even know.
Well, you do. And then, yeah, all 6 could be on the AP test.
This is news to me.
She told you, bro. She told us all that.
Huh.
The quiz that was immediately after the lesson, I said you didn't need to know it for that quiz. So you certainly could. We have 0 over 0. You could take L'Hopital's rule of this again. However, there is a way we could simplify this before we use L'Hopital's rule again.
That can go into
Secant squared x minus 1, it is a trig identity, is equal to tangent squared of x. So then, Okay, so this is equivalent. You still have 0 over 0 because tangent of 0 is 0. So your indeterminate form didn't change. However, this is an easier form to take the derivative of. Now, it is, though, you have to remember tangent of x quantity squared, so chain rule applies. So you, using L'Hopital's rule, you'd have the limit as x approaches 0 of. So with chain rule, it would be 2 times keep the tangent of x the same, times the derivative, which is secant squared of x, over derivative of 3x squared is 6x. It's still 0 over 0.
I wouldn't change.
Who makes this stuff?
Who made this function specifically?
Little hospital.
Okay, I'm going to continue this down here. Okay, so we can still apply L'Hopital's rule. We still have 0 over 0.
It's just gonna be something over 6.
But yes, now this will be the last time because your denominator will no longer be 0. Your denominator will be 6.
This function will finally be zero.
However, to find the derivative of the top, you need product rule and chain rule.
Oh, I'm not doing that. Can you just give us the answer?
Are they honest? They're gonna ask us what.
They could.
That's like 5 minutes of work.
This is how long are we gonna go? Yeah, I did ask them. It's like 15 minutes. There's so many steps where you
This
need.
one
They wouldn't
example has
dare.
not been 15 minutes.
I
You're right. It's been like
I don't
20.
know. Yeah, but let's be honest.
That's
It's
just
easy to do that.
okay, now what am I gonna do?
All right. So derivative, so product rule, derivative of the first is 2 times secant squared x. But for secant squared x, you do need the chain rule because this is really secant x squared. So it's kind of like what we had over here. So
Wait.
derivative of the outside would be 2 times secant of x just to the first power. And then times, yeah, the derivative of secant x. Does anybody remember what that is? Yeah, so, sorry, no, that's
Because he doesn't need to.
negative cosecant squared. You mean? That is the derivative of cotangent. So then, if I use the product rule here, I would have, for the first times second prime, I would have 4 times, here within this I have a secant squared because I have secant times secant. I'm also going to have tangent times tangent. So I would have a secant squared x and a tangent squared x. And then plus second times first prime would be secant times 2. So 2 secant to the 4th of x. All right, so the limit. Oh, I didn't write. We're still approaching 0. This is, yeah, we can actually find the limit. So, yes, tangent, as x approaches 0, tangent is 0, secant is 1. So this term is 0. This term is 2 times 1. So this term is 2. So it's 2 over 6, so 1/3 is the limit. That was brutal.
For 1.
Not everything in life is easy.
Got
Beauty
that.
of it, isn't it?
Yes, Ifrit. Okay. Question, Megan? Oh, okay. No, that's okay. All right, so right now, there are other indeterminate forms other than 0 over 0, infinity over infinity, but are there questions? I mean, I realize this was a long process. Are there questions on it, though? Maybe. The ones I passed out before. Maybe. I can look. At the very least, I could make another copy of one. All right, so then for the next example. So this, you can see, looks different. You do not have a quotient to begin with. So you have the limit as x approaches 0 from the right of x times natural log of x. So here, with limit rules, remember we have a product of functions, so it's like you're taking the limit of each function and multiplying the limits together. So if x is approaching 0 from the right, then the limit of x would be, well, I'm not taking the derivative yet, so I'm using a form of direct substitution. X would approach 0. As x approaches 0 from the right side, what does natural log of x approach? Not 0. Not 1. The natural log of x, the graph looks like this. So if x is approaching 0, the natural log of x is approaching negative infinity. So we can, but not in the form that it's written in. So in order, like I said, in order to use L'Hopital's rule, you have to have a function where the indeterminate form is 0 over 0 or infinity over infinity. You cannot say that 0 times negative infinity is 0, and you also can't say it's infinity. This is also indeterminate, but we can't take the derivative the way that it's written right now. So what you can do is you can rewrite this. Are you just hoping you're not able to do it?
Yes.
Oh. What you can do is there's two ways you can rewrite it. You can rewrite it as a quotient. Okay, so I'm going to show you both forms. So you can write this as, one way would be, because I'm going to write it as a fraction. What you're doing is you're leaving one of your two terms on the top of the fraction, and you're putting the reciprocal of the other in the bottom. Guys, if you're not following along with this, you're not going to know why I'm rewriting this the way that I am. So I could leave x on the top and then put 1 over natural log of x on the bottom. So this expression is equivalent to this, because in order to simplify this, I would multiply by the reciprocal, so I would multiply by natural log of x and get back to what I had. But now I have a fraction. It has to be a quotient, because for L'Hopital's rule, it has to be 0 over 0 or infinity over infinity. Otherwise, you can't use it. So then the other way I could write it is leave natural log of x on top and then put 1 over x on the bottom. So which way you do it, you have to try it out. If the first way you try it doesn't work, and you'll see what I mean by doesn't work, then you would try a different way. Because now you have to see, first of all, if L'Hopital's rule would apply. So say we tried this first one. If x is approaching 0, my numerator x would also approach 0. And then what does natural log of x approach if x approaches 0? If x approaches 0, natural log of x approached negative infinity. And if you have 1 over negative infinity, that approaches 0, because you have 1 over something very, very large. So now you do have 0 over 0. So you could use L'Hopital's rule. So if we apply it here, I'd still have the limit as x approaches 0 from the right of derivative of x on top is 1 over, now to take the derivative of 1 over the natural log of x. Nope. because you can't just take, if this would be a quotient, then you'd need quotient rule if you left it. Or you could rewrite this as natural log of x to the negative first. So then taking the derivative of this would be a chain rule. So it would be negative 1 times the natural log of x to the negative 2 times the derivative of natural log of x, which is 1 over x. So here's how you determine if I say wrote it this way first, is it going to work? Look at your denominator and think, okay, my numerator just became 1, but then my denominator became something very, very complicated. Let me just rewrite this here. Yeah, negative 1 over x times, natural log of x quantity squared. Okay, so now I'm no longer going to be able to use L'Hopital's rule because my top is just 1. And I already know if this is 1, my denominator, let me see here. Even in this denominator, I have 0 times, if x is approaching 0, this is times negative infinity again. It's indeterminate again. So I got an even worse form by doing it this way. Okay, that might happen. So if that happens, try the other way. If I rewrote it this way instead. So this is not good. This was not helpful. And you're only going to find that just by trying it. So it's not like I can just tell you, here's what you should do every time, because it's different. So say you rewrote it this way. Can I still apply L'Hopital's rule? The top, as x approaches 0 from the right, the top approaches negative infinity, we determined. If on the bottom you have 1 over 0, it's approaching, it's undefined. Undefined is approaching what? Undefined means your limit is approaching either positive or negative infinity. And since here, it doesn't really matter what the sign on the infinity is, since we're approaching from the right side, it'd be approaching positive. But if you get 1 over 0 or a number over 0, it means you're approaching either positive or negative infinity. So we can apply L'Hopital's rule for this. And I have the limit then as x approaches 0 from the right. Derivative of natural log of x is 1 over x. And then derivative of 1 over x, it'd be, negative. So, because this would be x to the negative first. So it'd be negative x to the negative second, which is negative 1 over x squared. And that may not look like a better form. However, if I simplify this, this means I'm really multiplying by a negative x squared over 1. If I'm dividing by that, I'm really multiplying by the reciprocal. And that means I have the limit as x approaches 0 from the right of negative x squared over x is just x. And now I can plug in 0, and the limit is 0. Okay, but you cannot say from the beginning, oh, 0 times infinity is 0. So I did x squared over x is just x. Okay. For the next one, I still want to do 14. We'll, because we're still keeping up or continuing, I guess, with L'Hopital's rule tomorrow, so we'll do 15 tomorrow. But 14, this is a same type of thing where you have the limit as x approaches infinity of x squared times e to the x. So if you took the limit of each of these terms individually, if x approaches infinity, x squared also approaches infinity, e to the x also approaches infinity. Infinity, or wait, no. Is that right?
Yeah.
Oh, that is right. I have a typo. That's why. This should be negative infinity. I'm sorry. You can. Aren't we done at 2:13?
Nah, we only got like, no, that's still not
So
enough
we
time.
have 5 minutes. This won't take 5 minutes. So,
Well, in student time, that's like 2.
well, if you keep talking, it will take 5 minutes. So it's supposed to be negative infinity. That is my typo. I'm sorry. So e to the x, if x is approaching negative infinity, what does e to the x approach?
Oh, that changes that.
That'll change it. It'll approach 0, yes. So this is the graph of e to the x. If x approaches negative infinity, the y values approach 0. So then, because again you have that same indeterminate form of 0 times an infinity, we can't say it's 0 based off of this. So you'd have to rewrite it. And again, x is approaching negative infinity, not positive infinity. In general, so I'm going to give you a helpful hint for this one. When you have a power function, so x to a power multiplied by e to the x, do not put the power function, so the x to the power, in the denominator, because as you can see here, when you do that, your powers on x in the denominator are going to continue going up, and we know the derivative of e to the x never changes, it just stays e to the x. So if you had e to the x, this is what I mean, if you had e to the x over, and then it would be over 1 over x squared, the top is going to keep being e to the x, and your denominator, your powers on x, are going to keep going up because they're in a denominator. So this route will not get you anywhere if you have a power function times e to the x. Instead, you want to put, or keep the x squared on the top, and then do 1 over e to the x in the bottom, which I'm going to rewrite this right away, not using L'Hopital's rule, but I'm going to rewrite it as x squared over, and then 1 over e to the x is really e to the negative x. Okay, so then I can use this form over here, though, to show you why L'Hopital's rule would work. Here, if x is approaching negative infinity, x squared would approach a very, very large positive number. And then we already said e to the x approaches 0. So 1 over 0, again, would approach either positive or negative infinity, but the sign doesn't matter. You just need to know that you have infinity over infinity. So if I now apply L'Hopital's rule, I'd have the limit as x approaches negative infinity of derivative of x squared is 2x, derivative of e to the negative x. Chain rule, so it'd be, it'd be e to the negative x times the derivative of negative x, which is negative 1, so negative e to the negative x. So you have to use chain rule because it's not just x, it's negative x. Okay, but then we have the same ratio we did before. The denominator is still going to approach either positive or negative infinity. The top is still approaching, in this case it's negative infinity because 2 times a very, very large negative number, so we can apply it again. And derivative of 2x is 2. This will be the derivative of e to the negative x again times negative 1, so it'll turn back to positive e to the negative x. And now you have 2 over an infinity, which 2 over something very, very large is 0. Okay, but if you have to show that it's 0, this is showing why it's 0. So we'll do 15 tomorrow. What that means, I think it's just number 28 if you're looking at the practice that you wouldn't answer because of 15. Otherwise,